to evaluate this trig integral, secant to the fourth of x, tan squared of x dx. And this one is just an application of using the trig integral rules you have learned up to this point in terms of what to do with specific powers of trig functions. But even if you forgot those rules, you can definitely figure it out from this. So keep in mind, whenever you have these trig integrals like this, you're either going to be doing u substitution or end up having to use a half-angle identity or something to fix them, so to speak. But you should always think about trying the u substitution first. So we only have two functions in this, either secant or tangent. So that means either u could be secant or it could be tangent. So if u were to be secant, that would mean the derivative of u would be secant tangent. But the problem is that the numbers don't work out here. We don't have enough secant tangents for everything else to work out appropriately. Whereas if we chose u to be tangent, the derivative of tangent is secant squared. And we definitely have a secant squared here. And with the extra secant squared, we could just use our trig identity. So the rule being that if you have an even number of secants, you always want u to be tangent of x, makes sense because the derivative of tangent is secant squared, an even number of secants. So what we want to do first is just use the identity. We know that 1 plus tan squared x is equal to secant squared x. So we want to turn one of those secant squared x's into this. We would have secant squared still left over, which is exactly what we need if we wanted u to be tangent of x. So what we can do is we can rewrite this as secant squared x times another secant squared x, which we're going to rewrite like that, and then times tangent squared x. And before we do the u substitution, let's go one step further and distribute this and combine all the tangents into one expression. We'd have tan squared x plus tan to the fourth x. Okay, now we're ready to do our u substitution. And hopefully, if it wasn't clear to you at the start, it is now, that it makes a lot of sense to say u equals tangent, because the derivative, secant squared, is sitting right here, and it'll work out perfectly. So we want u to equal tan x. Of course, then du is equal to secant squared x dx. And we have secant squared x dx right there. So our integral becomes, the secant squared x dx just becomes du, and if tan was u, then all we have there is u squared plus u to the fourth. And now this is just a basic integral we've done using power rule. So, to integrate, don't need the symbol anymore. To take the antiderivative of these, we're just going to use the power rule. So we're going to get u cubed over 3 plus u to the fifth over 5 plus c, because we have an indefinite integral. And finally, we're just going to plug in what we had for u, which was tangent x. So we have tan cubed x over 3 plus tan to the fifth x over 5 plus c, and that's our final answer. So for these trig integrals, I mean, if you feel like if it's worth it to you, you might as well just memorize what you do for each type of power. So if you have even powers of this or odd powers of this. But if you just know what the derivatives are, you can always just kind of figure it out by looking at the function anyway.